So let's now take a look at the energies. We looked at the wave functions. We know the other part of solving the Schrodinger equation is to solve for the binding energy of electrons to the nucleus. So let's take a look at those. And there, again, is another difference between multi-electron atoms and the hydrogen atoms. So when we talk about orbitals in multi-electron atoms, they're actually lower in energy than the corresponding H-atom orbitals. And when we say lower in energy, of course, what we mean is more negative, right? Because when we think of an energy diagram, that lowest spot there is going to have the lowest value of the binding energy, or the most negative value of binding. So let's take a look here at an example of an energy diagram for the hydrogen atom. And we can also look at an energy diagram for a multi-electron atom. And this is just a generic one here, so I haven't actually listed energy numbers. But I want you to see the trend. So for example, if you look at the 1s orbital here, you can see that actually it is lower in the case of the multi-electron atom than it is for the hydrogen atom. You see the same thing regardless of which orbital you're looking at. For example, for the 2s, again, what you see is that the multi-electron atom, its 2s orbital is lower in energy than it is for the hydrogen. The same thing we see for the 2p. Again, the 2p orbitals for the multi-electron atom, lower in energy than for the hydrogen atom. But there's something you'll note here also when I point out the case of the 2s versus the 2p, which is what I had mentioned that I would be saying again and again, which is when we look at the hydrogen atom, the energy of all of the n equals 2 orbitals are exactly the same. That's what we call degenerate orbitals. They're the same energy. But when we get to the multi-electron atoms, we see that actually the p orbitals are higher in energy than the s orbitals. So we'll see specifically why it is that the s orbitals are lower in energy. We'll get to discussing that. But what I want to point out here, again, is the fact that instead of just being dependent on n, the energy level is dependent on both n and L. So n is no longer that sole determining factor for energy. Energy also depends both on n and on L. And we can look at precisely why that is by looking at the equations for the energy levels for a hydrogen atom versus the multi-electron atom. So for a hydrogen atom, and actually for any one electron atom at all, this is our energy, or our binding energy. This is what came out of solving the Schrodinger equation. We've seen this several times before, that the energy is equal to negative z squared times the Rydberg constant over n squared. Remember, the z squared, that's just the atomic number, or the charge on the nucleus. And we can figure that out for any one electron atom at all. And an important thing to note is in terms of what that physically means. So physically, the binding energy is just the negative of the ionization energy. So if we can figure out the binding energy, we can also figure out how much energy we have to put into our atom in order to eject or ionize an electron. We can also look at the energy equation now for a multi-electron atom. And the big difference is right here in this term. So instead of being equal to negative z squared, now we're equal to negative z effective squared times RH all over n squared. So when we say z effective, what we're talking about is instead of z, the charge on the nucleus, we're talking about the effective charge on the nucleus. So for an example, even if a nucleus has a charge of 7, but the electron we're interested in only feels the charge as if it were a 5, then what we would say is that the z effective for the nucleus is 5 for that electron. And we'll talk about this more, so if this is not completely intuitive, we'll see why in a second. So the main idea here is z effective is not z. Don't try to plug one in for the other. They're absolutely different quantities in any case when we're not talking about a one-electron atom. And the point that I also want to make is the way that they differ. Z effective actually differs from the total charge in the nucleus due to an idea called shielding.